Previously, in the RH saga, we encountered the Riemann zeta function, and we said it's the simplest example of an L function. So what is an L function? There is a very deep theme at the heart of mathematics called duality. In linear algebra, you have vectors and their dual objects called functionals. In quantum mechanics, you have bras and cats. In group theory, you have conjugacy classes and irreducible representations. And in number theory, you have prime numbers and L functions. So this is a first very non-rigorous explanation. L functions are the objects that are dual to prime numbers. We will get to a much more precise definition of what an L function is, but first, today, we will simply look at two examples. The Riemann zeta function can be written as 1 over 1 to the s plus 1 over 2 to the s plus 1 over 3 to the s and so on. Here, the sequence of numerators is just 1, 1, 1, 1 and so on. A general L function can be written as a1 over 1 to the s plus a2 over 2 to the s plus a3 over 3 to the s and so on, where these numerators is some sequence of numbers. The numbers in this sequence are called the Dirichlet coefficients of the L function, and today we won't distinguish between the L function on one hand and the sequence of coefficients on the other hand. They contain exactly the same information. So here is one example of an L function. 1, 1, 0, 1, 2, 0, 0, 1. 1, 2, 0, 0, 2, 0, 0, 1. 2, 1, 0, 2, 0, 0, 0, 0, 3, 2, 0, and so on. Most sequences, like if I just wrote down some random numbers, 1, 1, 0, 2, 2, 2, 0, 2, that would almost certainly not be an L function. But this is one of those very, very special, almost magical sequences that happen to be an L function, or the coefficients of an L function. Can you see the pattern in this sequence? Could you, for example, predict the next entry or the next 10 entries? Here is a more complicated example of an L function. 1 minus 1 minus 2, 1, 0, 2. 1 minus 1, 1, 0, 0, minus 2. Minus 4, minus 1, 0, 1, 6, minus 1, 2, 0, minus 2, and so on. What is the pattern here? These two sequences are examples of motivic L functions. And that means, roughly, L functions constructed from polynomial equations. The first example is the L function constructed from the equation x squared plus 1 equals 0. Let's label this equation with the letter k. The second example is the L function constructed from the equation y squared plus x times y plus y equals x cubed minus x. We'll label this one with the letter E. And when I say constructed from, I'm referring to a certain machine that takes an equation as input and produces a sequence as output. If you want to treat this machine as a black box to begin with the help of Sage, again, just install Sage for free or go to the SageCell website. For the first equation, just type this one line of code. The equation, you can sort of see here. Here it says what the variable is. This specific equation defines something called a number field, and we're asking for the first 20 L function coefficients of this number field. For the second equation, you can use this code. Here, we don't see the actual equation. Instead, we use the shorthand or label 14.A5. This equation defines something called an elliptic curve, and we're asking again for the first 20 coefficients. And you can change this to any number if you want more. The main goal for today is to study these two L functions, explain how the sequences appear from the equations, and find the underlying patterns. And these patterns will be instances of what mathematicians call the Langlands program. Before we jump into the specifics of the two sequences, I want to take a step back and show you the LMFDB, the L functions and modular forms database. In the LMFDB, you find L functions and objects that give rise to L functions. You see elliptic curves here, number fields. In the Hall of Fame, you have the Riemann zeta, the Ramanujan delta function, and there's a lot more. But let's go to the universe page in the top left. Here we see this quite famous picture of the connections between the different worlds entering the Langlands program. On top we have the L functions. L functions can be viewed as independent entities on their own, but often we think of an L function as being constructed from some other object. And these other objects, I like to call them primal objects. In this picture, we see the three major classes of primal objects. Motives on the right, automorphic representations on the left, and Galois representations down here. So each primal object gives rise to its own L function. We have two motives already, because any polynomial equation can be viewed as a motive. So K is a motive. That was the equation x squared plus 1 equals 0. And E is also a motive. The motive K has its L function, L subscript K, and similar for E. And these are the two sequences of numbers we just saw. Now, the conjecture known as Langlands reciprocity says that whenever you have a motivic L function, so an L function coming from the right-hand side, you can find an automorphic object from the left-hand side that gives you the same L function. If you have a motivic L function and you manage to prove that a corresponding automorphic object exists, then your L function has what's called an analytic continuation and a functional equation. This in turn means that it makes sense to talk about the Riemann hypothesis for your specific L function. All of that is a story for next time. Today, we'll go back to focusing on these two examples, K and E, and their L functions. Okay, let's have a look at our first L function. The mysterious sequence for this L function was 1, 1, 0, 1, 2, 0, 0, 1, and so on. Let's put these numbers in a table. Here we have the index n, 1, 2, 3, 4, 5, 6, 7, 8 on the top, and the sequence an, so a1, a2, a3, a4 at the bottom. Let's just look at this sequence for a few moments. The first 2 is here at a5. Then there is actually also a 3 at a25. And the initial entries are 1, 1, 0, 1, 2. I want to give a simplified explanation of how this sequence is constructed from the equation x squared plus 1 equals 0. You may recall that the equation x squared plus 1 equals 0 is used to pass from the real numbers to the complex numbers. What we do is that we start with the real numbers, we throw in a new number, which we call I, with the property that I squared plus 1 equals 0. Using the two operations addition and multiplication, you can then generate more numbers, and all of those numbers together is what we call R adjoined I, or with a special symbol, C. That's the complex numbers. Now we can do the same thing again, but this time starting not with the real numbers, but with the integers. So we have the integers, we throw in the new number I as before, and we think of everything we can generate with multiplication and addition from that. This set of numbers is written Z adjoined I, there is no special symbol for them, and they are called the Gaussian integers, after the mathematician Gauss. The complex numbers can be visualized as a two-dimensional plane. The Gaussian integers is then the subset of points with integer coefficients. For example, 3 plus 2i or 2 minus I, so all the intersection points of the grid are Gaussian integers. Definition. The norm of a Gaussian integer a plus bi is simply a square plus b square. For example, the norm of 3 plus 2i would be 3 square plus 2 square, that's 9 plus 4, so that's 13. Let's now compute the norm of a few small Gaussian integers. The norm of 0 is 0. We don't care about that now. The norm of 1 is 1. The norm of I is also 1. The norm of 1 plus I is 1 square plus 1 square, that is 2. The norm of 2 is 2 square plus 0 square, that's 4. And the norm of 2 plus I is 5. And we keep going like that. Now let's count. How many points have norm 1? Well, there is 1, 2, 3, 4 points in total, but there is a rule that when one point can be rotated into another by a 90-degree rotation, then they count as the same point. So these 4 points, they just count as 1. And this rule comes from the fact that multiplying by I is the same thing as rotation by 90 degrees. So for norm 1, there is 1 point. For norm 2, there is also 1 point. For norm 3, there are no points. For norm 4, there are 2 points in the picture, but they count as the same. For norm 5, there are 2 points. For 6, there are 0 points. Same for 7. And now, perhaps, you recognize this sequence. 1, 1, 0, 1, 2, 0, 0. If we look at 25, then there are 3 points. This sort of explains how the equation x squared plus 1 equals 0 gives rise to the sequence 1, 1, 0, 1, 2, and so on, that is the L function of k. So we have passed from the equation to the L function. Now, there are 2 major challenges. First, it's still not so easy to see how to compute the next entry or the next 10 entries of the sequence without doing the actual counting of Gaussian integers. Is there a recursion or some kind of rule that generates the next entry from the previous ones? Second, we got the L function somehow from the equation x squared plus 1 equals 0. Is there a way to get straight to the L function without using the equation? Look at this. What I do is I write the sequence here on top, and then I follow a procedure. This procedure is a loop where I first subtract and then I copy the result. I take the first top element and subtract everything that's written below. There's nothing below, so 1 minus nothing is 1. Then I distribute copies of 1 all along the first row. In the second column, I take the top element and subtract everything that's written below. 1 minus 1, that's 0. And I distribute copies of this 0 all along the second row in jumps of 2. third column, I take the top element and I subtract everything that's written below. 0 minus 1 is minus 1. And I distribute copies of this minus 1 all along the third row in jumps of 3. And so on. In the fourth column, we have 1 minus 1 and 0. In the fifth column, we get 2 minus 1, that's 1. Then 0 minus these numbers, that's 0, and so on. Let's animate this. Now, do you see a pattern? Look at the diagonal. 1, 0, minus 1, 0. 1, 0, minus 1, 0. 1, 0, minus 1, 0. This is it. This is the pattern. And I can now reconstruct the L function using this simple periodic or recursive diagonal, just by running everything in reverse. So I fill in the diagonal first, then I distribute copies along the rows as before, and the opposite of subtraction is addition, so I just sum each column upwards to get the top element. The sum of 1 is 1, the sum of 1 and 0 is 1, 1 plus minus 1 is 0, 1 plus 0 plus 0 is 1, 1 plus 1 is 2, and so on. Now, we did not use the equation k at all. We have reconstructed the L function by using a much simpler object, the diagonal. Now, this diagonal is actually an automorphic L function. It's one of the simplest automorphic L functions in nature. And we have reconstructed the original motivic L function using this automorphic object together with, in some sense, the Riemann zeta function, where the coefficients are just 1, 1, 1, 1, 1, 1, 1, 1. The Langlands program. We need one more example. Recall the sequence coming from the equation E. The equation was y squared plus xy plus y equals x cubed minus x. The L function was 1 minus 1 minus 2, 1, 0, 2, 1 minus 1, 1, 0, 0, 2, minus 4, and so on. The machine that takes an equation and gives you a sequence was described in the previous example using this counting of Gaussian integers. In this example, I'll describe the same machine in a different language. Now we will count solutions to the equation mod p for different prime numbers p. Whenever you have a polynomial equation with integer coefficients, you can count the number of solutions mod m for any positive integer m. Let's start with mod 2. And in this example, it's faster if we factorize both sides of the equation first. Mod 2 means that x and y can only be 0 and 1. And all computations are done mod 2. So for example, 1 plus 1 equals 0. The right-hand side is always 0, since either x or x plus 1 is 0. Therefore, the left-hand side must also be 0. That happens either if y is 0, the first factor, and then x can be anything, 0 or 1. Otherwise, if y is 1, the bracket must be 0, and this happens only if x is 0. All in all, mod 2, there are 3 solutions. When y is 0, x can be anything, and when y is 1, x is 0. And the number of solutions, 3, is what we wanted to find. That was mod 2. Now let's count solutions mod 3. X and y will be 0, 1, or 2, and all computations are done mod 3. The right-hand side is the product of 3 consecutive integers, and one of them will be 0 when we work mod 3. And hence the entire product is 0, that's the right-hand side, so the left-hand side must again also be 0. Now, either y is 0, and x can be anything as before, or y is 1, then the bracket must be 0, which means x is 1. Finally, y can be 2, again the bracket must be 0, and x has to be 0. All in all, there are, let's see, 5 different solutions to the equation mod 3. The next prime would be 5, and the counting of solutions is similar, it's just more casework. If we do the work, there will be 5 solutions again, mod 5. But let's cheat and do this with Sage. Now we need a large table. Top row, labeled n, is just 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. In the next row, labeled p, I've put the primes 2, 3, 5, 7, 11, and 13. And under these primes, I'll write the solution counts we just found. Mod 2, there were 3 solutions. Mod 3, there were 5. Those we did by hand. And then from Sage, we get 5, 6, 11, and 17. I'll just label this row with solve for solutions. The goal is to construct the L function from these solution counts. And we do this in 3 steps. First, for the primes, we just subtract the prime itself minus the solution count. 2 minus 3 is minus 1. 3 minus 5 is minus 2. 5 minus 5 is 0, and so on. The last one is 13 minus 17, and that's minus 4. For any equation, there may be certain primes that are different. We call them bad primes. And for this equation E, I can compute that the bad primes are 2 and 7. And that computation is straightforward. I'm not showing it here. Step 2 for the table is to do the powers of 2, the powers of 3, and the powers of 5, so the prime powers. For the powers of 2, 2 is a bad prime, and the rule for bad primes is that the values for the prime powers should be a geometric sequence, starting with 1. So I have 1, then minus 1, then 1 again, and then minus 1, and this would continue alternating between 1 and minus 1 for all powers of 2. For powers of 3, 3 is a good prime. That means the rule is slightly more complicated, but there is a recursion for the values at powers of 3, which in this case boils down to taking minus 2 squared, that's 4, and subtracting the prime 3. And that gives me 1 for the value at 9. Step 3. For the remaining values of n, we compute by multiplicativity. So for the number 6, 6 is 2 times 3. So to compute the number I need, I take minus 1 times minus 2. That gives me a 2. For 10, 10 is 2 times 5. I need to take minus 1 times 0, and that is 0. And finally, if I decompose 12 into prime powers, I get 4 times 3. So I need to take minus 2 times 1, and that gives me a minus 2. And now we have constructed the L function from the solution counts mod different prime numbers. And this procedure is close to the general recipe for any equation. Primes first, then prime powers, then all the other numbers. Okay, we computed the L function from the equation. But again, we have the same two major challenges as in the previous example. First, is there a rule of some kind that lets us compute the next entry in the sequence? And second, we got the L function from the equation. Is there a way to get straight to the L function without using the equation? We need coins. Here I have red coins, denominations 1, 2, 3, 4, 5, 6, 7, and so on. The rule is unlimited supply of each type. Blue coins, 2, 4, 6, 8, 10, 12, and so on. let's say this is dollars. $2, $4, $6. Yellow coins, 7, 14, 21, 28, and green coins in multiples of 14. Okay, say I want to pay you $1. In how many ways could I do that? Only one way. A red $1 coin. Say I want to pay you $2. In how many ways could I do that? Well, I could give you 2 of these, or 1 of these, or 1 of these. All in all, 3 different ways. How about $3? Let's see, I could pay you 1 of these, or this one and this one, or I could use these 3, or I could use these 2. All in all, 4 different ways. Let's put all of these combination counts into a table. Actually, we'll start from $0, and I can give you that in exactly one way, which is to not give you any coins at all. $1, one way. $2, 3 ways. $3, 4, and then it's 9, 12, 23, 32, 55, that's a Fibonacci number, 76, 122, and so on. Now, you know the usual multiplication table with positive integers on both sides, down here and up here. 4 times 3 equals 12, and so on. Maybe you say this is boring, but look at the diagonal sums. They are 1, 4, 10, 20, and maybe it's an interesting exercise to work out the pattern. But leave this aside for now. Let's construct a new, more exciting multiplication table using 2 rules. First, one side consists of these coin combination counts: 1, 1, 3, 4, 9, 12, 23, and so on. Second rule, the diagonal sums should be the sequence 1, 0, 0, 0, 0, and so on. The first diagonal sum should be 1, so I need a 1 here. That means a 1 must be on top, since 1 times 1 is 1. Now I get 1 times 1, 1, 1 times 3 is 3, 1 times 4 is 4, and so on all the way. Now the second diagonal sum should be 0. That means I need a minus 1 here, and that gives me a minus 1 on top. I can fill out the second column, minus 1 times 1, minus 1 times 3, and so on. The next diagonal sum is 0 again, so I need a minus 2. That forces a minus 2 on top, and I can again fill out the rest of the column. Next number has to be 1. That gives me a 1 on top, and we keep going. Aha! Look at the top row. 1 minus 1 minus 2. 1, 0, 2. 1 minus 1, 1. 0, 0, minus 2, and so on. We have used the coins to construct the L function. And again, the remarkable thing about this process is that we constructed the L function of E without using the equation in any way whatsoever. Now, maybe you say that this coin counting gets very time consuming for larger n. Like already for like $20, the number of combinations is more than 3,000. But it is possible to rephrase this coin business into the language of generating series. And with that toolbox, it's very easy to compute the sequence very, very far. For those of you who know about generating sequences, the generating sequence for this L function can be written as the product over all n of 1 minus q to the n times 1 minus q to the 2n times 1 minus q to the 7n times 1 minus q to the 14n. And of course, you recognize the numbers 1, 2, 7, and 14 in the exponents. So, to summarize, we had an L function coming from the equation E, and we managed to construct it also by a completely different method. In fact, this generating series is an automorphic object. More precisely, it's a modular form. And it gives you the same L function as the equation, and the equation was an example of an elliptic curve. I want to zoom out and say something about the bigger picture. The Langlands program today consists of a bewildering number of different branches. But the original main branch, which is directly relevant for L functions, can be called global Langlands over number fields. And this main branch consists of two major themes. One theme is functoriality, and we'll get back to that some other day. The other theme is reciprocity. Reciprocity expresses the idea that any motivic object has a corresponding automorphic object with the same L function. The objects on both sides of the correspondence have a dimension, sometimes called a rank or degree, depending on the context. And Langland's reciprocity is a statement about objects of any dimension, 1, 2, 3, 4, 5, and so on. The correspondence between elliptic curves and modular forms, which is quite famous because of Fermat's last theorem, is part of Langland's reciprocity in dimension 2. This was what we wanted to convey with our second example, called E. In dimension 1, Langland's reciprocity includes something called Artin reciprocity. And the simplest case of Artin reciprocity is quadratic reciprocity that Gauss discovered. He called it the golden theorem and found, I think, 8 different proofs. Now, our first example today, K, is a special side case or supplement to the law of quadratic reciprocity. So in some sense, it is the simplest of cases of one-dimensional Langland's reciprocity. If you want to read something very accessible about the Langlands program, I would recommend this absolutely beautiful book by Edward Frenkel called Love and Math. In the table of contents, you see all kinds of amazing things like the grand unified theory and at the end, searching for the formula of love. There is one thing I'd like to show on page 88, and here we have this equation which is similar to the one we worked with today, and you also see this generating series quite similar to the one we obtained from the coin counting. Finally, imagine that you know that you'll be stranded on a deserted island and you can only bring one person. And suppose you don't care about love or friendship or survival or anything like that. You just want to learn as much as possible about the Langlands program before you starve to death. Then the right person to bring along is Matthew Emerton. If we go to his webpage at University of Chicago and click Papers and Preprints, there is an incredibly nice survey of Langlands reciprocity there, if you want a much more technical and rigorous introduction to the subject. Here is the abstract, and you see almost all of the words we use today, like reciprocity laws, L functions, relating arbitrary motivic L functions to automorphic L functions, and so on. So many of the words we use today are rigorously defined in this paper.